All right, we're going to start the afternoon session. And first up, we have Griffin tell us about pasta.
Okay, thanks for sticking around till afternoon. Um, I'm going to talk about our new observing program called PASSTA. You notice that there's AEON in the name of PASSTA, that PASSTA acronym, which is why I thought I should talk at this workshop. This is meant to showcase like you've all spent so much work building this amazing system where you can control multiple observatories at the same time and coordinate observations across them. And this is the kind of thing that you can actually do with it, right? So here's a no, couple of examples of the science. I'm not going to mostly bore you with the science, but let me just show you why this type of thing is important. So type 1a supernovae, for example, we know that they are white dwarfs exploding in a binary system, but that's about all we know. We don't know what they're in a binary with in most cases, and we don't know how they actually explode. How does the white dwarf ignite? And really, the cutting edge, the frontier of figuring out the remaining answers about what type 1a supernovae are is very early and very late spectroscopy. Um, you can see at the top couple of panels here are early spectra showing both in the optical and infrared, showing very unique features, almost relativistic velocities within like about a day of explosion on the left-hand side. And then this unburned carbon on the right-hand side showing that potentially it's an incomplete explosion of the white dwarf. There's some remaining carbon from the white dwarf. In the bottom panel, at very late times, nebular spectroscopy, showing um, oxygen, for example, placing a unique constraint on what that explosion can be, that it leaves oxygen there. Um, and line profiles throughout this whole optical to near infrared range showing the symmetry of the explosion and many other things that I won't go into here. But the point is simultaneous optical and near infrared spectroscopy can provide really important clues both early on and late in the evolution about what these supernovae are. Likewise, type 2 supernovae, the other most common type of supernova, we know that they're exploding red supergiants, and we're pretty sure now that there's a lot of circumstellar material around them in some kind of dense, confined shell or some other shape. But we don't really know how much CSM or how it's produced. How did it get off of the star in the first place? If you get very early spectroscopy, you see these narrow emission lines that indicate the composition and density and potentially the radiation field that's ionizing them of the circumstellar material, and that evolves on like day time scales, even hour time scales. And at very late times, nebular spectroscopy of type 2 supernovae can show you, for example, again, oxygen emission lines that correlate with the mass of the progenitor to tell you what type of star it was that exploded, um, all the way from the optical into the near infrared, as you see here. Also, at late times in the near infrared, you probe dust production, carbon monoxide being shown there. And also you can see a few other line profiles again that tell you about the asymmetry of the explosion once you can see all the way through it. So also in this case, the frontier is to get full optical to near infrared spectroscopy very early at high cadence and very late at the nebular phase. So because the observing campaign, the observations we have to do is the same. What's best is if we just unite this into one big program and try to get complete optical to near infrared data sets on all nearby supernovae. Um, this light curve plot on the right hand side is showing kind of the extremes of type 2s. They vary a lot more in brightness than type 1as. The black and the red are both type 2 supernovae. And type 1as, which peak almost at the same place, but you can see they do very different things potentially at early times. Uh, so within 50 megaparsecs, we can reasonably uh, we can follow the supernovae around peak with 1 or 2 meter telescopes. But for these very early times, we need much larger telescopes, 4 meters or more. And also at very late times, as it's fading, we need 4 meter or more telescopes. And that continues if you want to go even farther into the nebular phase. But the idea is that early on, we should get basically spectra every day for the first few days, and then follow it less quickly during the photospheric phase, and then at late times, 100 days, 200 days, maybe 400 days or something, pretty low cadence after that. So to do this, you see we need cross-observatory coordination. This cannot all be done. Well, you could all do it with an 8-meter telescope, but nobody's going to give you enough time to do that. So what we need is when the supernovae are bright, we should follow it with small telescopes, and when the supernovae are faint, we should follow it with big telescopes. So the program that we've designed here is for this very time-sensitive, deep, early spectroscopy. We'll use either on the SOAR 4-meter telescope, TOO mode if it's a classically scheduled night, or time-critical EON mode if there's an EON night that night. We also have a Gemini program, which we can do rapid TOOs, depending again on the hemisphere and exactly how bright this is. During the photospheric phase, we can use Las Cumbres Observatory most of the time, which gives us both amazing light curves and regular spectroscopy with fluids. And then at very late times, we again switch to those big telescopes. We can use SOAR in the regular EON Q mode at very low priority, Gemini standard TOO or Q, depending on how early you know what the target is, and of course other institutional facilities that we have access to at very, very late times if you need a bigger telescope, Keck, MMT, SALT, name your favorite big telescope on the Earth. So of course, I can't believe I'm the first one to show this map at a Las Cumbres conference. I thought this was a requirement, so I put it in here, but the dots, the green dots are the Las Cumbres sites. Many of you are familiar with this, probably all of you. But I wanted to point out here that these are also EON sites, if we treat it as one big observatory, right? Gemini is here and in Hawaii. SOAR is in Chile. And in blue, I've noted where the major time domain surveys are right now. So another thing you need to think about is if you're trying to get spectroscopy very urgently from a new discovery, you kind of want to be shortly to the west of that survey. And you see that our facilities are pretty well positioned for that as well. So this is the concept. Let me now explain the acronym. The PASSTA program is the Public EON Spectroscopic Survey for Transient Astronomy. Basically, the idea is that we will take advantage of the EON dream that everyone here has been working to create and apply that to get data sets on all nearby supernovae, right? Collect complete data sets on basically every event within 50 megaparsecs. So it consists, the way we had to do this, of course, because as we were just discussing at the unconference, all of these telescopes are, even though there's some coordination, you have to write separate proposals for them, for example. So PASSTA is the name of my SOAR program that I PI'd, but the greater PASSTA collaboration consists of the Global Supernova Project that Andy leads on Las Cumbres, our own 3-year SOAR program that was just approved, like a 3-year NOIR Lab survey program that began on August 1st. Jen Andrews and Dave Sand, who now left because he didn't want to hear my talk, have 3 years large and long programs on Gemini that are very related science and can get both low and high resolution optical and near infrared spectroscopy for fainter targets. And we also made sure to unite all of the SOAR partners. So UNC, Michigan State, Chile, and Brazil all have time on SOAR. And we wanted to also coordinate our SOAR observations across all the partners so that we don't both trigger on the same supernova at the same time. There's a small number of nearby supernovae, and we should try to do that as efficiently as possible. And I should mention also that although these are not part of the spectroscopic survey, technically, we have a couple of survey programs that I'm a co-I on. One is led by Dave Sand to shadow the LSST fields with DECCAM. I'll talk about that at the end if I have time. And we have a new firm survey, infrared survey for supernovae led by Charlie Kilpatrick. These are both actually part of EON as well, right? On the Blanco telescope. And those are both really important sources of targets for us. So the public part of the PASSTA acronym is referring to the fact that we will release all of our classification spectra immediately on the TNS. We are working on our procedures and all that, but the goal is that we will release classification spectra before the end of the night in Chile. The reason we want to be so prompt on that is because in these situations where you have spectral features varying on few-hour timescales, somebody may want to get another spectrum of the same target in South Africa or the Canary Islands or something if it's equatorial. And so you really need to know what type of supernova that is to plan your next spectrum. Or you may have a program that's only for one type of supernova. You may have certain interests. So you want to know that on less than a 1-day timescale, kind of what the classification is for something so nearby. And we have committed to releasing even our follow-up spectra on SOAR and GMOS. The other Gemini instruments are a bit harder to do on a short time scale. But we're going to release all of these data in real time, so like not waiting until we write the paper, but they will be on a few-day time scale. After we reduce them, we'll put them all on WiseRep. I made this very basic website just so that there would be a website. Don't expect a lot on there, but if you want to read the details of like our collaboration guidelines and what we've proposed to do, you can check that out. Who's actually involved in this collaboration? It's a large number of people. I don't expect you to read all of these, but hopefully you can pick out your friends in here and talk to them about it. One of the major points I want to make is that we need a worldwide collaboration to be able to be operating at all times of the day on a regular basis, right? So we want to, of course, in the US, we're going to be watching for targets all the time during our daytime and triggering them when necessary, but we also want people to be able to trigger things during the night in Chile, right? And so for that, we have collaborators in Australia, Hawaii, China, India that can help with this type of thing, and potentially even do TOO observing if needed. In some cases, you have to provide the observer for SOAR, so you might need to actually log on and do the observations. And of course, these are the people that I've recruited so far, but the program is open to anybody. So if any of you happen to be interested in this type of science, you're welcome to sign up for tasks to do in the collaboration and join, and we can figure this all out together. We put out an astronote a couple weeks ago inviting the community to join, and we've had some interest actually already so far, but please advertise that to anybody else you think might want to know it. And of course, I have to, as part of my PASSTA talk, say that my acronym, of course, was inspired by PESTO, the Public ESO Spectroscopic Survey for Transient Objects, which technically ended on Saturday night, I believe, their last observing run on the NTT after a decade of doing this regular transient spectroscopy. They're now talking about whether they can extend it for like another 2 months or something like that. So maybe they haven't quite ended yet, but certainly this is coming to an end because they're building their new instrument, Son of X Shooter, which is going to go on NTT pretty soon. But they did release an astronote saying the final question mark ePesto spectroscopic classification. Okay, so very relevant to this workshop is the infrastructure it takes to do this. Of course, there's all this human infrastructure, building the collaboration and having people know what they should, how they can contribute. That's very important, but software infrastructure is very important as well. We're working on building it in real time while also running the program. Our current infrastructure is a little bit disjointed. So in terms of getting the alerts, we're relying on the Saguaro TOM, which Dave mentioned briefly earlier today, but I'll go into a bit more detail now. We built this TOM for gravitational wave follow-up for our Saguaro program. But while we were doing that, we were like, of course, this is super useful for everything else we're doing too, for supernovae. We're already doing all of this host galaxy association. This is how we know if things are within 50 megaparsecs or not. We're doing checking against point source catalogs to make sure we don't have variable stars or AGN contaminating our sample. We're aggregating photometry from the TNS, ZTF, Atlas Force Photometry server. I mean, anyone else that will give it to us, but those are the only ones that are public right now. Someday it will be Rubin as well, once we have an alert stream to listen to. And then we have just a filter for things within 50 megaparsecs that are observable by SOAR. We get a Slack alert in our new Slack workspace telling us, here's a target, you should probably trigger on it. And of course, there's some human intervention after that. This is how we get the alerts. Now let's talk about what we do after that. This is what the Slack alerts look like right now, if you're curious. Very simple. And that link then will take you to more details about the object. We already receive alerts for anything reported to the TNS. We don't have a direct alerts going for ZTF things that are not reported to the TNS. Our assumption there is that most nearby supernovae will be reported to the TNS, like through their bright transient survey, for example. We would like to do that, just haven't had time yet to actually check the ZTF stream directly. And of course, we would like to check the LSST stream directly as soon as it comes online. But very important for this actually is we should not rely on just one alert stream, right? Some of our best constraints on which things are detected within 1 day of explosion or 2 days of explosion come from combining the alert streams. So we might have ZTF have the discovery data point, but Atlas had a non-detection right before that, 12 hours before or something like that, or I should say vice versa, I think. That really gives you the tightest constraints on the explosion. And right now we do that all ourselves in the TOM, but really I think this is something that the community needs to think about, especially, we're talking about building both ZTF brokers and now LSST brokers, but those should be the same thing. They shouldn't be two separate brokers, right? And we should include everything in the TNS too, because there's a lot of other surveys happening. So we are working right now, Maura's working hard on this already, upgrading the supernova exchange, which we have used for a long time in the Global Supernova Project, to be able to handle all of the needs of this program as well. You can already schedule SOAR observations through SNEX, but it is not as seamless as it is for the Les Cumbre spectrographs. For example, if we wanted to just in one click say, get me 3 spectra over the next 3 nights, that is not possible. You have to actually do it 3 times. And there's like a bit of a more complicated form that most of which is irrelevant to us. We would like to be able to do the actual classification tasks comparing to templates within the TOM, so because we have a very decentralized collaboration and we don't want people to just do all of this on their laptops and then all that information to get lost. It should be all in one place. We would like to be able to very efficiently release all of our data. So there should just be a button in the TOM saying, send this to the TNS, send this to WISE-Rep. We're almost there, actually. Not quite tested yet. And of course, because there are so many people, so many collaborations and meta collaborations within this project, we need to make sure that the permissions work correctly in the TOM toolkit in the Supernova Exchange so that everybody can see data they need to, but not data that they don't have access to. In terms of the observatory infrastructure, we are hoping to be like the test case that can push SOAR to working even more efficiently for time domain astronomy. It's already one of the best facilities in the world for time domain observations. But if we could do things like submit our finder charts via API rather than having to click and upload them to a Google Drive, that would really help, because then we could automatically generate the finder charts and there wouldn't need to be any humans there. If we could know when the Q nights are by a method other than checking our email, that would be very useful. So that's supposedly what Heroic is going to do for us. I hope that happens very soon. Sounds like it is going to. I already mentioned this as a question earlier on Slack. Knowing which instrument is available to us, so we could say, most times I actually don't care what instrument we get the spectrum from. Any optical spectrograph is fine. I'm more worried about the time sensitivity of it than the specific wavelength sensitivity. So I would like to be able to just submit a request for Goodman red camera or blue camera, whichever is available, and whether that happens on the SOAR side or it happens within our TOM by figuring out which is available and then submitting the right thing, doesn't matter to me. But we would love for this kind of stuff to happen from our program. Here's an example, not of the SOAR form, but a form that we built for the MMT, which functions in a very similar way. This is kind of what we would like to see for SOAR, right? Where we just click spectroscopy, optical spectroscopy, or infrared spectroscopy, essentially is what that is. Put it in exposure time, choose the wavelength setting, which is actually even simpler for SOAR than what you see here. Choose the program, check TOO, and upload your finder chart. This is all in the TOM already. And then the data processing side. So let's say we get all of these observations we want. We want to be able to very quickly and routinely reduce the data and release it doesn't need to be the final version that's released. Quick look data is still very useful, but I would like it to be not totally wrong, because that is embarrassing. But we've had some issues before with wavelength calibration in like the official Goodman pipeline. We've looked at different ways of handling that. It's complicated, I think, because of flexure in the instrument. That's my understanding. Some members of the collaboration have had more success with Pipet, and so we're looking into that as well. I haven't used Pipet for this yet, so I'm not the right person to ask, but if anyone's interested, I can point you to the right person. Classification tools, as I mentioned, we want everybody in the collaboration to be able to do this. So we want people that have not been trained to use SNID or Superfit before to be able to run it easily. And the new versions of like the Python-based version of Superfit and SNID Sage seem like really good ways forward. We're looking into those and writing up like an official manual after you get data, what you should do. Updating template libraries with these very early spectra. We've seen this a few times before within our DLT40 collaboration, where we actually get one of these really early spectra within 12 hours of explosion, let's say, and it looks like nothing else in the template library. That's the hazards of being at the cutting edge, I guess. But we actually have so many spectra now from the GSP and from DLT40 that we should update the template libraries for these classification tools, and that should be able to help us in the future. And again, I would like for this to kind of be a way to train students around the world to do all of these tasks that are very important to transient astronomy. So those of us in the collaboration that are experts in certain things, one thing or the other, can write a manual, actually maybe hold a Zoom training for everyone else in the collaboration so that everyone has a chance to participate. So to kind of summarize, the idea is that AEON can be the ultimate time domain follow-up machine. That's in quotes because I think it was part of the title of either Dave or Jen's Gemini program. But it's not just Gemini. This whole thing is the time domain follow-up machine, right? Where you have multiple different classes of telescopes gathering whatever data set you need on every single nearby supernova. There's not that many, but in the past, we've only been able to actually get such a data set on 1 or 2 events. To get this on 10 or 15 per year would be really a huge increase. And I think you can see from what I've described so far, right now, humans do everything. We watch for the alerts, we click all the buttons, we trigger the telescopes, but we're actually very close to having this be fully automatic. I think you can imagine going from what I described in the past few slides to just having the target be identified if it meets some criteria. We get a Slack message, but at the same time, it just triggers the telescopes directly. And then the data gets ingested into our TOM, gets reduced by some automatic pipeline behind the scenes. You run the classification tools on it, and it gets posted to TNS all before I wake up in California. That's the dream, right? And we're very close to that. ZTF Bright Transient Survey is doing something like this right now with the SED machine. We love their work as well. It's just a brighter threshold than what we would get here, right? So we could increase the sample size of things that this happens for pretty significantly. We can potentially schedule follow-up months in advance if we have the right logic in here to respond to the data that we get in, decide what kind of follow-up needs to be scheduled on which telescope, and just have that happen all behind the scenes and be monitored by humans rather than having humans figure it all out and press the buttons. And of course, we would love to add additional facilities to this. It's not just optical and near infrared that matters. I have a Swift program for exactly the same science, and we trigger it regularly on this type of thing. In my mind, Swift is almost an AEON because I can trigger things. It essentially runs as a queue without any human in the loop. And that's been very, very useful for us. We can kind of do it with MMT. It's just that the optical spectrograph is not always mounted. I have a Keck program. So Dave Sand at Arizona has an MMT program. I have a Keck program also for the same science to do TOO observations of young supernovae. But right now, yeah, I would love to talk to Keck people about how we can submit TOOs through this kind of AEON system rather than through the current Keck system in the web browser. But anyway, we'd love to add these other wavelengths, later phases, increase the sample size by going to more distant targets. That's all fair game. So if people have thoughts about how we can do that, please talk to me. So for observatory people in the room, my dream wish list, I know not all of this is possible on a short time scale, but we want to operate in Q mode all the time. So whatever you can do to add more Q nights, that helps us be less disruptive to everyone else. We really don't want to be triggering SOAR TOOs every night for 3 nights in a row, even though that is what we propose to do, because that's the only way you can do this. As I mentioned in the unconference session just before this, I would love to be able to do OR requests. Give me either SOAR or Gemini, whichever one has good weather and the instrument is not broken, or the optical spectrograph is mounted. That would be incredibly useful for us. Growing the collaboration in terms of observatories, research groups that want to do the same science, and even research groups that want to do other science but want to use all the infrastructure that we built. I'm open to doing all of that. How's my time? Includes question. Okay, then I'm done. Thanks for listening. If you want to talk about how your observatory or your research group can fit into this, Slack me, email me, or talk to me. Thanks a lot.
Hi, I'm Hannah. I'm from Noir Lab. I'm the lead developer for AEON for SOAR and Blanco.
Great.
And I can let you know, at least right now, that Cesar has his hand raised, so he's probably going to say the same thing as me. We do publish our AEON nights in advance for each semester. We know when they're going to be. We know if it's going to be blue cam or red cam.
Yeah.
And if you need on Slack, I can send you the resources for you to be able to check that. If that's
how do you publish them?
It's on our webpage, so I can go ahead and find the links for you.
But like as a text file, right?
Yeah.
Yeah. So I have that text file, but what I'm saying is, and occasionally it changes throughout the semester too, because more nights are added and stuff like that. And of course I get the emails, but what I'm asking for is for it not to rely on me checking my email to know that, right? Like the system should be able to query some API and say, okay, I know that now this new Goodman Blue Night has been added or whatever. I think that would be very useful for because right now there's a single failure point with me getting that text file as an email.
Yeah, I'll go ahead and see if Cesar has something to add about the subject, but I do think that that's a great idea.
Yeah.
Would be a good implementation.
Yeah, Cesar, go ahead.
Hi, Griffin. Oh, sorry. Great talk. Thanks. It was really good to see all the stuff great stuff that you guys are doing. Yeah, like Hannah said, we have that. I think we having the schedule published in an API friendly form is something that we just didn't consider before.
Yeah.
But now that you requested it, that's definitely something that we can get to work on.
Right.
So that it's you can just update automatically and you have a single point of access through the API where you can get the most updated schedule and for the nights and what whether you have Goodman Blue or red. So that's fine. Another thing that I wanted to comment is on we had a student that we hired to look at our Goodman pipeline. And actually, because one of the things that I wanted to compare was how was the Goodman pipeline doing compared to other software. And we had him run it against IRAF, for example. But one of the other things that he did was run it against PyPy.
Mm-hmm.
And so we do have, and he had to do quite a bit of work on PyPy in order to make it Goodman friendly and get it to run all with Goodman. But that's all. I just wanted to let you know that that's something we already done, and he has the appropriate version of PyPy that runs with the Goodman data and with the 400 line grading and that kind of thing, which is the one that is most often used. So if you want, I can, put this guy in contact with you or your team or something. because it may save you guys some time if you
Yeah,
want to just get to run the Goodman spectral wave pipette right away.
yeah, that would be really great if you put us in touch. That we'll definitely talk to them. So Charlie Kilpatrick is the one who I think he said the same thing, is that he had to put in a lot of work to get Pipette to work correctly with Goodman. But
Yeah.
he has some kind of working version. So I mean, I don't know. I haven't used it either, but if we get these two people in contact, I'm sure we can figure out what the best procedure is and write that down somewhere.
Yeah.
That's my hope.
Yeah, and we're trying to get also the pipeline to work better. So yeah,
Yeah, great.
we'll continue in touch about that. Okay,
Great, thank you.
great. Thanks.
All right. Thank you, Griffin. Let's thank Griffin again. And our next speaker is Stephen Potter. And yeah, if you just hold that, and he'll tell us about the Intelligent Observatory.
Oh, thanks very much. It's great to be here and to be able to share my work with you guys, and thanks for the opportunity for allowing me to give this presentation. So I'm Steve Potter. I'm from the South African Astronomical Observatory, and I'd like to talk to you about a program we started probably about 7 or 8 years ago now. So back then, about 8 years ago, we asked ourselves the question, what do we need to do in order to advance astronomical operations and research at our observatory? What do we need to do to make sure that we remain relevant in the next few decades and globally competitive? And so there we formulated a program. We called it the Intelligent Observatory Program. And the reason why we gave it that name will become clear just now. So this is a quick bullet point list of the questions, kind of our wish list that we derived back then 8 years ago, and you'll recognize some of these questions as I read them out. So we wanted to move our observatory into an operation scenario where we could submit observation requests at any time, and not just at the call of semesters. We want to be able to do science on any time scale. So following up transients, doing snapshot exposures once a night for 6 months, or any type of time scale. We want to be able to observe at our site in Sutherland, but also in Cape Town or maybe anywhere in the world. We wanted to switch from not only doing manual observations, but queue scheduling observations and maybe service observations. And then also move into an era where we can respond to alerts or other computer-generated requests. And basically be in a position where we could better coordinate science across all of our telescopes in this so-called era of multi-messenger astronomy. And I'm just going to go back a slide because I forgot to put in context what the observatory is. So this is a photograph of the observatory. We're a national facility, so our time on our telescopes are open to anyone in the world. In the corner there, top right-hand corner, is the Southern African Large Telescope, so it's a 10-meter class telescope. And we operate that on behalf of a partnership of international institutes. South Africa has a 50% stake. We then have 3 workhorse telescopes, a 1.9 meter and 2 1-meter telescopes. They're fully owned and operated by the observatory. And then we have a whole host of telescopes that we operate or host on behalf of other institutes that we have. We either full partners in, or we have a percentage of telescope time on. And you can see in the top left-hand corner there, there's 3 1-meter telescopes of the Las Cumbres Observatory. But we have telescopes from Japan. We have 2 infrared telescopes, telescopes from South Korea, from Germany, from the UK. There's a couple of Russia telescopes there, and Polish telescopes as well. So we have a whole host of telescopes. And so back then, these are the questions we came up with. Sorry. And I've put green ticks there because this program was launched about 8 years ago, and we've now, to some extent, achieved all of those questions. And we focused on our 3 workhorse telescopes. And to just give you an idea of the challenge, the telescope in the middle is a 1-meter telescope. It's about 10 years old. The telescope on the left is another 1 meter telescope. It's about the same age as me. I'm not going to tell you my age. And the telescope on the right is a 1.9 meter telescope, and that telescope is about the age of my mother. So we needed to upgrade the hardware and the software services on all three of these telescopes in order to achieve those goals we had. And we've done that. All three telescopes are now fully remotely able to control them remotely from anywhere in the world. So no one needs to be in the dome at all, from complete power down to power up, observe, and back down to shut down again. We've gone a bit further than that with the newest telescope. This one is now actually fully robotic, a fully autonomous telescope. And we made use of the OCS, Observatory Control Software of the Las Cumbres Observatory. So that saved us 20 years of development work, I think, to get that telescope as a fully autonomous telescope. So that one now is fully autonomous. And between those three telescopes, we deliver spectroscopy, polarimetry, and imaging, and high cadence, high speed imaging modes as well. And in addition to software upgrades, we identified a few targeted hardware updates as well. So for example, on the 1.9 meter telescope, we identified if we just made a simple upgrade to our acquisition box, we could co-mount two instruments at the same time. And this meant that we moved from a scenario where we could only have one instrument on the telescope for like several months at a time, to now we could switch between imaging and spectroscopy as many times as you like during the course of a night. And that was a simple targeted hardware upgrade, which had massive significant implications on the operations of that telescope. So moving forward, we're now looking at upgrading our 1.9 meter telescope. This telescope is over 80 years old. We're now moving, it can be remotely operable, but now we're looking at making it fully autonomous. And this is work in progress, but we are at the stage where we're fine-tuning. These are kind of all the bullet points that you need to address in order to make a telescope fully autonomous. So all of these are at the stage where we're fine-tuning them. So I think this might be quite remarkable to get a telescope that's over 80 years old to be fully autonomous, I think. So that was our vision 8 years ago. And earlier this year, we felt like we need to pivot, I suppose, and come up with a new vision. So this is the Intelligent Observatory Vision 2. And again, we asked ourselves, what can we do to advance SAO operations into this so-called fourth industrial revolution? How can we make use of the new tools that have come about? And we've also wanted to look at the whole science cycle as well. So it's not just automation of telescopes and software services. How can we start looking at modern day technologies to come up with the original science idea and going all the way to the final publication? So we started looking at that as well. And we were very fortunate at the beginning of the year that we formed a new 2-year partnership with the Hartree Centre in the UK. So the Hartree Centre is a facility of the UK Science and Technology Facilities Council. And the Hartree Centre, their expertise is in supercomputing, data science, and artificial intelligence. So thanks to a very generous grant from the STFC, we have a 2-year partnership with them where they will help us incorporate these new technologies into the operations of the observatory. So I just want to highlight a couple projects that we're working on together with them. We've called these, one is called the Telemetry Project, and one is called the RAG Project. So the Telemetry Project basically is, let me give a bit of background context first. So maybe 15 years ago, we had several technicians per telescope. Today, that's now completely reversed. We have now more telescopes than we have technicians, including software developers and scientists. So we wanted to, one of the projects we identified to help with this shortage of resources, we call the telemetry project. And this is basically, we want to create a system that logs and analyzes telemetry data from all of our instruments on all of our telescopes across the whole plateau, with the objective to perform health checks and faults analysis, predict necessary maintenance in advance, also to produce advanced data products to complement scientific data, and to investigate when there's equipment failure. So, and in order to do that, we needed to upgrade all of our software services, and even create software that creates telemetry data. And we needed a system, a database basically, that starts ingesting all of that telemetry data. And then hopefully once we've done that, we can start using some AI technologies to do all of those blue bullet points. And so as of now, I guess a month ago, we now, 3 of our telescopes with their instruments are now, we're recording telemetry data from them. And we created this system. It's called the Intelligent Observatory Telemetry System, or IOTS for short. For a while, we were toying with putting the letter D in there somewhere, but that got rejected. So we just kept with IOTS. So we have this database. We haven't yet developed any AI tools that analyze it, but now we have a database. We at least have a web interface that we can at least manually interrogate this database. And we already have 3 telescopes, the 40-inch, the 74-inch, and the SETI, the 1-meter telescope, are in there, and various other services from across the observatory, like the weather data. So through this web interface, you can, for example, for the past 7 days, you can plot the weather state, the humidity in blue, versus the dome shutter open status. So here you can check, did the fully autonomous telescope, did it really close when the weather turned bad? So you can do this manually. And of course, we would, using more automated tools, we want to put more of an alert service on this. So we're having a service that would monitor these sort of parameters, that would alert a technician or standby staff that, you know, things are not doing what they're supposed to do. As part of the telemetry project, we also have web cameras in every dome, and we continually record the audio from these from the telescopes. So now, you know, in the olden days when we used to work in the telescopes, if something made a peculiar noise at nighttime, you would stop what you're doing and go and investigate. But in these days of remote observing on autonomous telescopes, there's no human in the telescope anymore to notice when things go bump in the night. So we've started recording audio, and this is an example of where the blue is not actually the audio volume, it's called the audio error deviation. So we've already given machine learning technologies a set of audio from the telescope, and from which it's learned what the normal sounds are. And then in real time, it uses this machine learning algorithm, learns what's a normal sound, compares it to the live audio feed, and produces what's called an audio error deviation. So again, this could now form part of an alert service, where if the error deviation goes above some threshold, because it doesn't recognize a sound that hasn't been there before, it could alert a technician or standby person to say there's something wrong. And on this particular night, you can see something happened in the middle there. We started getting this repetitive pattern. And this was because there was a leak in one of the one of the pipes from the air compressor. So the air compressor was switching on and off a lot more frequent than it needed to, because there was a leak. And it didn't trigger the error deviation here, but from your eye, you can see that there's something that's not quite right there. And so very quickly, as part of the telemetry project, we've also now, for these 3 telescopes, we created a searchable science archive of data from those 3 telescopes for all those instruments. For 2 of the telescopes, this data goes back 15 years, I guess. and this will complement the telemetry data. Okay, so that was the first project. The second project I mentioned that we're focusing on together with the Hartree people, we're calling the RAG project. So this is all about what do we do with all of our documents and information that we hold at the observatory. We have decades of documents amounting to hundreds of thousands of documents. There's so much documentation that it's now become absolutely impossible for anyone to extract information from it. No one uses the documentation anymore because they wouldn't know where to look. It's an impossible task. And we have documents, wiki documents, Google documents, and then documents that are just stored on the server somewhere. So this is a kind of a picture of what our document management system might look like if it was real paper, I suppose. So, but there are now new technologies, there are new opportunities. So we're all familiar now with the large language models that have been released in the past few years. There's also another technology called the retrieval augmented generation. And it's the combination of these two tools that now are giving us new opportunities. New opportunities that if we can get this to work, this will finally make information capture and storage really worth it. And we all hate writing documents because we know at the back of the minds, someone's never going to read our documentation and our information is going to be buried amongst all the other documents. But if this works, then our information is going to be available. But using these technologies, there are other things we have to make sure we get right as well. We have to address things like intellectual property and data security. And then how do we go about collating, gathering all of these documents? So I should say there are some solutions out there already. Google Gemini, Google have, for example, the Notebook LM interface, which is fine, but if you're uncomfortable with sharing your documentation, your intellectual property with big corporations like Google or whatever, then you don't want to use that. You're going to have to develop these technologies in-house yourself. So we've started on this, so you don't need to read this, but as a couple of weeks ago now, we've released our first internal version of a intelligent document information server. So far, we're only working on the documents for our intelligent observatory. We haven't ingested all the other 100,000 documents yet. We're still trying to get the whole workflow started. So this is an example where, so I'm going to give you two examples of when you get this technology to work, this is the sort of thing you can do. So you might recognize this. This kind of looks very similar to the ChatGPT interface that you might be familiar with. So it's the similar technology. It's an open web UI interface. So this is all open source software. So we asked the question, what are the web addresses for the Makudi instrument on the LSST telescope? So this is a simple factual question. All you're asking for is please retrieve from the documentation the answer to this very specific question. And it gave the answer. It's given an answer describing its attempt to find the answer in the documentation. And then it's also listed the actual documents and links to the documents where it thinks that information is held. So you can go back and you can confirm the accuracy of the knowledge of the answer that the system has given back, because you can't just rely on a large language model. That's not going to give that sort of information. And then at the other end, you can do something more complex. So here I asked the question, describe the LSST telescope in the form of a poem. So here it's doing two things. It's using the documentation on the telescope, so it'll search all the documentation that mentions the LSST telescope, and it will use the back-end large language model to take that information and create a poem out of it. So this is a bit of a funny example, but if you read it's a bit of an internal poem. So if you read the poem, you will see that the poem is completely constructed of kind of in-house software technology kind of phrases. You can see it. There's no way a large language model could have done that on its own. This required that kind of in-house knowledge that's embedded in our documentation. And of course, it also gives you a list of the documents in which it got this information from. So it's a funny example, but you can imagine once you have a system like this working, you can write things like annual reports or statistics reports or any sort of reports or essays or whatever, or sets of instructions. So for example, you could ask it things like, please write me a data reduction recipe for dummies for the spectrograph on the 74-inch telescope. And it will go and do that. It will find the information in the documentation. It will tell you the document, and it will convert any instructions that are already available in the documentation into a dummy version of it, because that's what you've instructed it to do. And okay, I think I'll stop there. Thanks.
Excellent. Thanks for keeping on time, and we have time for questions.
Hi, nice talk. Daniel Deveau, CFHT. Did you require special hardware or anything powerful to train the system to your documentation like that?
Yeah, the training does, yeah, the ingestion of all that documentation is going to take a lot of processing power, because there we do have hundreds of thousands of documents. But if you have hundreds of documents, then no, not really. It's something you can do on a high-end PC in no amount of time at all. And using this RAG technology as well, it's quite a relatively easy process to add new documents. As you produce new documents as you go along, you don't have to re-ingest everything all over again. You just ingest the new document, and that will be incorporated into what's already been ingested.
All right, another question.
Hi, Austin at LCO. I'm curious about the audio detection. Can you play back the sections that were detected? And if so, can you like call someone that's on call and like play it back for them over the phone?
Yes, absolutely. So in the telemetry database, we're only recording the deviation error, but the raw audio is also recorded as files on the archive. So you just need to go back to the correct time that the audio occurred, download it, and listen to it.
Any other questions?
Hi, I'm curious about, so you mentioned about using the AI to do like data reduction recipe. So I've been training some AI to do this with the cake data reduction. So there's a lot of documentations from the cake observer archive. But then for AIs, they usually, if they don't know something, they'll hallucinate. So have you encountered a lot? And if so, how do you solve that?
Yeah, that's a great question. And this is exactly what this RAG technology is addressing. So you're giving it the documentation that the documentation, it's not just relying on the large language model. So the large language model was created, whatever, by ChatGPT or Gemini, whatever they ingested. So you can imagine the large language model as an expert that doesn't have very good memory. But then if you give that expert all of your local documents, then it has access to all of your documents as well. So it's that combination of these two technologies, the large language model and the documentation that's given the answers. And in addition, this provides you, it will give, as part of the answer, it will give you the documents from which is derived the answers to the question. So you can go back and double check that it's not hallucinating, or you can go back and check for any details on on the answer as well.
And can you remind us again what the technology was used to generate this?
So it's RAG for short, RAG. It's short for Retrieval Augmented Generation.
But I mean, is that a general term? Is there a specific like brand of thing? Like you mentioned Google Gemini, but like what large language model are you using, and then how does it pair with your local documents?
So you can use any large language model. So Retrieval Augmented Generation is the high level name of this technology, but there are several. You can use any large language model, and there are also several software that you can use to ingest the data, chunk the data, and all that sort of thing. There's a whole sequence of software technologies that get your documentation into a data kind of vector database format that's RAG ready. And there are several solutions for that. A lot of it is open source. A lot of it, some of it is proprietary, but it's a lot of open source out there.
Did you experiment with different companies' versions of this until you found the right one?
So as I said earlier, we've partnered with Observatory. They're the experts in this, and we're kind of their sandbox. So they're learning as they go along as well, because some of these technologies have only been out for a few months. And just as you think you've learned one technology, another better one comes along. And, you think, do you start again, or do you commit to the end, as it were?
Now I'm wondering if we can partner with them ourselves. Okay. Are there other questions? Yeah.
I want a question about your telemetry system. So, I work in space-based astronomy, so telemetry is kind of like a normal thing for us.
Sure, yeah.
I was curious, the system that you built, did you build it from scratch, or did you use existing tools to build that? Because there's a lot of systems that have been built for space use that are kind of people who built stuff for operating satellites have realized that telemetry is just a useful thing. And there's a lot of open source packages out there to do this kind of telemetry monitoring. Is that what you're using, or is it in-house?
No, that's a great question. So a lot of the work went back to the software itself, the telescope control systems, the instrument software. They all had to be upgraded to just give out telemetry data, because that never existed before. That was the biggest, most time-consuming part, actually, is going back through all of your software and make telemetry data. And then we just put it into a database. We didn't look at any space-based telemetry systems, but we did the SALT telescope. They developed over the course of 15 years their own telemetry system and database. So we just copied their design. So that's why we were able to do it quite quick with such small resources. But now the whole analysis of telemetry data, that's what we're starting on now. Now we have the telemetry data available. How are we going to, what sort of tools can we start using to probe?
My advice would be, you're not an island here. There are lots of people doing this, and you may not be familiar with it because you're in your own particular silo.
Sure.
There's a lot of other.
Yeah, okay, I didn't think of that. Thanks.
All right. Well, let's thank Steve again and get our next talk started. Okay, our next talk is from Cam Wipper.
All right. Good afternoon, everyone. I am the last one, so congratulations. You made it to the end of the day. I hope it's finished off pretty strongly here. So I want to tell you about Kealahou and AEON. This is upgrading CFHT's QSO system for this LSST era. So just a bit of a primer on CFHT, as some of you may not be totally familiar with CFHT, since it's not primarily used within the U.S. community, though the U.S. community does have access through the University of Hawaii. So CFHT is one of the observatories on Mauna Kea. We're a 3.6 meter primary mirror there, and has a classical equatorial mount. And if you've seen Palomar, you've basically seen CFHT. Last year, we celebrated 45 years of science operations on Mauna Kea. We've been doing Q observing for over 20 years now, and we've been remotely operated from our Waimea base facility for about 15 years now. The instrumentation at CFHT is fairly wide as well. We have wide field imagers, both in the optical and infrared. Same thing for spectropolarimeters, as well as an IFTS named Sept. Also, one of the things we like to talk about is our in-house processing pipeline. So all the instruments have full in-house pipelines that produce fully reduced science survey data. In the case of some instruments like MegaCam, within minutes of observation. Some of the ones take maybe a day or so to get the first look data out. But unlike some other facilities that don't provide the reduced data, CFHT does. So the key part of this talk is about Kealahou. So Kealahou is our end-to-end QSO platform. Kealahou is a word from Alelo Hawaii, the indigenous language of Hawaii. That means the new path, the new trail, the new way. And what Kealahou consists of here is a single page web app, along with a API server and database there. This includes we call K1, which is our phase 1 proposal and submission review system. K2, our regular phase 2 science program management and data access system, has integrated user management and authentication system, as well as internal QSO operations tools and data bridges between our Kealahou and our legacy system, which operates in parallel, as not all of our instruments currently are transferred over to use Kealahou. And I'll note the system was designed and built in-house at CFHT. Our first instrument was Spiru, our infrared spectrograph, back in 2018. We currently support our 3 main instruments, Spiru, Esperance, and MegaCam. And then we replaced our previous North Star, which was used for proposal submission, with K1 in 2022. So a little bit about the infrastructure for Kealahou here. It's your classic kind of 3-tier design here. It's deployed across 2 sites. So we host implementations of both our summit as well as our base facility. That's mostly for redundancy as well as sort of just data security. So the front end is kind of the web side of things is built using an Angular framework. The back end is Java-based with an API, protocol buffers, and gRPC, other technologies there. And finally, the database is a 3-headed cluster that uses MariaDB. And finally, the software is built, tested, and deployed through a self-hosted GitLab repository and CI/CD pipeline. So a couple of things we've done recently with Kealahou. We recently rolled out what we call SNR mode observing capabilities for MegaCam. This allows for on-the-fly predictive SNR-based observing, which instead of basically specifying an exposure time, we specify an SNR, and the system will automatically determine, based on sky conditions, what the exposure time will need to be to reach your goal. We also have some user collaboration tools. Both K1 and K2 have an invite-based system, which allows all the users to grant access to their proposals and programs, including the science data, to their collaborators and students, all within the application itself. There's some bulk handling tools within the UI now for bulk upload of large target lists, as well as duplication of observations and that sort of thing for faster management of your programs. And finally, we're working on an ongoing effort to integrate a new instrument into Kealahou. We're working on combining our 2 spectrographs, Spiru and Esperance, and to be co-mounted on the telescope to allow basically joint observations from basically the right near the UV all the way into the infrared. And this combined instrument is called Veneo Keao, and we expect that next year. So what's most relevant, though, to this gathering is our integration to AEON. So in addition to this work, we've also are working to working on integrating into AEON. We've received funding as part of the grant that brought this workshop together to join AEON as part of AEON Plus. As you know, Rachel here is the PI of that program. And basically the 3 activities here, these are the 3 things that from the grant itself that we are committed to as part of our participation in the AEON Plus project. Basically expand and secure the APIs to allow basically Kealahou to talk to AEON, implement a new rapid target opportunity capability, as well as publish and document our APIs. So in order to do that, there's a few steps here. So we're looking at once the API work is completed, users will be able to submit targets, observation requests through to Kealahou from AEON through the R API. This will include both fixed and moving targets. And also included in this is the implementation of an RTOO capability. And this will reduce TOO observation delays from hours to days. Currently, we have a cutoff 5 p.m. that night for any requests for TOOs. And this will allow us to basically cut that down to from minutes to possibly even seconds from the request comes in to when we can slew the telescope to the target. And finally, although we utilize the Kealahou API internally, in a few minutes I'll demonstrate the software itself, and basically the entire web front end uses the API to communicate with the application. We do not currently have that available externally. Part of this project, we will develop and publish this API for external use. And as you've likely gathered already, this AEON and RTOO will play an important role in ensuring CFHT's sort of participation in this current era of time domain astronomy. So looking at our timeline for this work, we're tentatively planning on announcing our initial fixed targets integration, something like the 2026 B semester. That would mean we're opening the call for proposals likely in February. So that's our initial target here. We're shooting for that for initial AEON integration. Moving targets would follow sometime around 2027B, a year later or so, with the RTOO capabilities then following a year later, which we'd make available sometime around August 2027 or so, an initial call for proposals. This final API definitions and releases then planned for the fall of 2027 as well. So this timeline is aligned with our NSF grant and our global development schedule. As I mentioned, things like Veneo, Kealahou, other projects that we've tried to get everything on the same wavelength with. So what's next after that? So I did ask Google Gemini what CFHT in the future might look like. I'm not sure about giant robot arms, so maybe we'll leave it to the humans for a little while longer there. But we do have some sort of plans for after AEON here, after this current development cycle. This is sort of our Kealahou future outlook. We're certainly looking at automatic queue scheduling, potentially even autonomous observing, which I think some of you are familiar with. Implementation, as was noted previously there by the things like AI and this use of large language models, and the idea of spinning off open sourcing K1 or Kealahou, so it could be available for the broader community. So before I move over to a bit of a demonstration here, I do want to mention sort of a few of my colleagues here in the audience, Dr. Daniel DeVost, as well as software engineers Chris Usher and Conrad Holmberg. We're all here this week, and we're definitely happy to chat with any of you who have any questions for us this week. We are tentatively planning to have a little discussion on CFHT AEON integration tomorrow during our unconference session. So if you're interested, please join us there. We do have some sample code, test code, implementations you can play around with our API, and as well as some of our application, and take a look, see what you think, and hopefully we can work on some initial steps in getting that AEON integration happening tomorrow as well. All right, so with that, I think I'm going to switch over from the slides here to a little demonstration of the Kealahou software itself. So just bear with me for a moment while we switch out of this. All right, so let's see if I can do this without tweaking my neck here. All right. So what I want to do is just take you through our Kealahou application, sort of from basically proposal creation through to data access here. So For the most part, you'll be sort of taking the place of a PI who's going to use the system. There'll be a few steps in here that are on the administrative side that's sort of only available to CFHT staff, and I'll mention those as they occur. We'll also use this on our test instance here. So for those worried, this is not happening on a production server here. Make sure I type this in right. All right. So this is our regular login page here. You can create your accounts and contact us all from here. We do have public tools available, so things like user guides, how to use all the site, all the instructions. Those are all here as well for both K2, the program management, as well as K1 information on calls for proposals. All that sort of stuff is contained here within the public documentation. But let's sign in here. All right, so once we're in here, basically if we're going to submit a proposal, what we would do is head on up to the top menu bar here. We can see all the options here, K1 proposals, K2 programs, operations tools, and I'll show a few other things in a few minutes. The first thing I'll do, I'm just going to change. I'm not a big fan of the orange here, so let's go to some green instead. All right, so this is sort of a list of some proposals here. So I do have one to show you here, but if we're going to start something brand new, we would just hit right here, start new proposal. So same, as you've often seen on proposal submission, you have your calls that are currently open, semesters, all that sort of thing. Scroll down, upload science justifications, technical justifications, all that sort of thing. Select your abstracts. So I'm just going to go back to one that I pre-filled out here. So we're not spending so much time filling that stuff out. We can hit edit here. So here's our proposal. It's all filled out. We have instruments selected, abstracts, justifications, targets there. You can upload targets. It has a resolver here. So if we just try something, let's see. Hit resolve. It'll pull our data down, found the target, link target, fulfills our target data out from the database there. Configurations are all there as well for the instrumentation. This is for Esperance on our spectrographs. And then the collaboration interface. So if you are your collaborators, you can type their email address in here and it'll send them invites and they can join the proposal in which they can help. They can see everything here. Once your proposal is ready, you can go over and you can submit it. So if we hit here, we'll hit submit. Those are our parameters. We'll submit that proposal and it's there. So now at this point, you submitted your proposal at CFHT. A bunch of my colleagues have just gotten an email. That's just why this one says ignore, because it's not a real proposal that's come in. So we can go over to CFHT staff, then we'll then go to operations tools. You can head over here to proposal admin. You hit 25B, and this was engineering. And fetch, there's our proposal we just submitted. Have our timestamp. I can move this to proposal review. And then earlier I configured some proposal review, so you can use the system to conduct a full review of proposals, whether you're external, internal or external. So if you're, say, we have a whole community in France, they use this software to perform their reviews. The review admin is here. So I've come over previously and I've gone down and I've assigned myself as the science and technical chairs for this review. The engineering 25B there at the bottom. I want to invite more, I could. I can also just manage the chairs. You can see there, I'm the chairs of both of those reviews. Which means if I come over here to my review, I can hit manage reviews here. 25B. And there's my proposal that I just submitted. I can then view the proposal. I can download it. Here's all the information that I submitted. It does generate a PDF view of the proposal as well. So if I need to download a PDF version of this, share it offline, I can. It's all generated here. It has my target list, my information, who submitted it, how much time, all that sort of thing here. I can then also assign it. So if I want to invite here, I could type in, I want, say, my colleague Chris to review it, type in his email, let him know that how long he has to review the proposal, and then he could submit his reviews through here. Once the review is complete, the information will appear here in some of these review sections. So this one will say no reviews yet, but if you had reviews here, they would appear there. Finally, at the end of this process, you can come back down to proposal admin here, 25B engineering. And then I can come over here and I can press accept the proposal. And now that proposal has been accepted, and we can now create a science program. So again, come over to operations tools. I can go create programs, come down 25B, engineering. And finally, we have here is this engineering programs that are created, and I can come down. Here's that proposal that I just submitted that was accepted, and so I can and I can load, and then the information from that proposal is all pre-populated here. I just have to select the things like the grade and the rank, and set the time there, and I can down hit create. I'm not going to hit create here. I've already created a test program, but just want to demonstrate how that all works. So I'll integrate it and can immediately create a science program this way. From here, we then come to some of the test programs. So if I select here, these are now I'm now back the user. I have my science programs. I can load up my science programs, and they are here again. So here we have, this is your regular phase 2 interface, and we have all of our target list here. I can say I want to modify a target here. It's all there. View the footprint. It'll demonstrate where that target is with a finding chart here, instrument overlay. Here I would upload moving targets through an ephemeris file. Use AstroRes for that. Here we have the instrument configurations. And again, here you can configure all of your parameters, all of that. And as I remind you all I mentioned earlier, this web interface uses the API. So if you can configure it on this web interface, you can configure it through an API as well. That's what we're working to publish to the broader community. Finally, down here at the bottom, we have the observation groups. These are the actual observations sent to the telescope, which we create at the end. Here we have the name of the target, the position, the template. So that's the exposure times, the filters, dither patterns, and then it calculates the charge time for that observation to the program. Once your OGs are ready, it would then go to the queue to be observed. Now, the same software, we have observing tool here. So I'm going to load up a test account here. So this is what our observers would log into each night, and they would use this to actually conduct the observations during the evening. Press observe here, and it should be a test queue here. Yep. And so add this to the observing tool. It'll load this up, and here is the observations ready to be observed. Plot of where the targets are in the sky there, along with the telescope map there. And you can see if there's a particular issue with an observation, it won't let you observe that particular OG there as well. So once you're ready, you can just hit send selected here, and that would send the observation through to the telescope. Once that's done, as I mentioned, it would be processed through the queue, observed, and then the observer would give it a grade. And then finally, you would access your data back in your observing program. Go back to my program. Down at the bottom, I have the exposure section here. Here's a list of all the data that I've achieved per exposure. You can see here all of the parameters. We have the information. We have image quality requested. We have the image quality from the images, sky background, SNR, whatever you need to know about your image. Right up here is your data access key. This is how you download your data. And you have both the quick look data So take you to the raw just web directory where you can download your actual images right from the interface here. Or you can use some of the information here to set up an rsync or a wget or something like that, just to automatically download your data straight to wherever you want to have your data. So with that, just a quick demonstration here, sort of from proposal all the way through to data access of the system. And as I mentioned, the future for AEON, you could use the same system, but you will be able to submit all your observations, your targets through the API to the interface here, and then access your data like that. So I think with that, maybe I think we'll 9 minutes for questions. So let's wrap it up here.
All right, excellent. Time for some questions.
Hi, that was a very cool demonstration. I think this whole functionality is really awesome. I had a quick question about when you were resolving the target and like searching for targets based on target names. Where, like, how do you guys access that information? Is it just through something like Sinbad? My question would be is for supernovae, we've got the like astronomical transient name, but also a lot of them are reported with the internal name from various transient like surveys. So is that something you guys have thought about, or is there plans to deal with the fact that we have a lot of targets that have multiple names?
Yeah, so that's a great question. So yeah, we do use a Sinbad query to grab the name. So if it's a name, an object that is previously existing within there, it'll grab that based on any of the names. For objects that aren't in that database or because they're brand new or something like that, basically the system would return an object not found, and you would just input that as a basically manual input. And so you can put your coordinates in manually. And the reason we do a linking, that allows us to link it to a Gaia object. And that basically we have a kind of a master database of objects based on Gaia ID. And that's why we do that linking. But for new objects that don't have that, yeah, it would just be, we call basically a manual target, and it goes in like that. Yeah.
And we have a question online. Go ahead.
Yeah, thank you so much for your wonderful talk. I wanted to ask about the RTO program. So I had a question regarding that. So you mentioned that you moved to SNR from exposure time for the alerts, and so when you do TO follow up, would that be based on SNR or would that be based on exposure time?
So that would be up to basically the requester. So if they want to use one of our instruments that has SNR modes available, they could request an SNR mode observation, or they could request a fixed exposure time observation. So we offer both modes. Both are available, and it's up to the user to decide what they prefer to use.
Okay, got it. Thank you so much.
Great. Other questions? Yeah.
Forgive me if this is naive, but in a time domain context, I might not know my target until the moment it happens. So how does that affect the workflow that the very nice workflow that you've just demonstrated?
Sure, yeah. So in our plan for the AEON integration here is that, let's say you get an alert somewhere and you want to send it through the AEON network to us. You do that through what we want to build with AEON, which is the AEON lib integration, all that sort of thing. Basically, your target would be injected to our software through the API, and it would appear in that target list here as you could basically, and then you can build your OG manually if you want to do through the UI here, or we're planning on having an option where once you trigger that, it automatically, you can look for pre-configured observant templates here, pre-configured instrument configurations. You can link it with one of those and send that across. In that case, what would happen is it would create an observation automatically, what we call an observation group, and that would get sent to the observer. And so basically, once it's triggered, it would go straight, pop up on the screen of the night operator, and they could basically decide at that moment to just slew away and go to that target right away. So definitely this is the full manual workflow, but as part of this, we want to, especially for the RTOO, to more automate that process to basically cut down as much time as we can.
Okay, other questions? All right. Well, let's thank all of our speakers today.
And thank you all for a really successful first day to this workshop. Just one announcement before we wrap up for the day. That is, everyone who is speaking or presenting tomorrow, could you kindly upload your slides to the shared drive? You'll find the link on the Slack channel as before. And we will wrap the session up here today. We will restart back here again just before 9 a.m. tomorrow morning.
The 30-minute slot is not 30-minute for talks. We have to have some time for questions. So is it 25 and 5 or something like that? But just keep that in mind when you're uploading your talks.
Thanks, everybody.